What we just saw with the summation notation is actually what the motivation is for the Riemann sum. The word Riemann there is actually the last name of a famous mathematician. Basically, in a Riemann sum, we want an approximation of the function using n rectangles on an interval a to b. The notation we're going to use for the subintervals is going to be first subinterval starts with x1 and ends with x2. The second starts with x2 and ends with x3, and so on and so forth until the nth subinterval starts with xn and ends at xn plus 1. Notice that since we're using n rectangles, we need n subintervals. Each subinterval is going to be of the same size. We label that as delta x, meaning how much did x change in each subinterval. Because we want to make each the same size, the size will be b minus a over n. Whatever the distance is from a to b, we're going to divide that into n rectangles. So each subinterval is going to have size change in x. This symbol here is delta. Each subinterval has size delta x. Each rectangle will have assigned area depending on which rule we're using. If we're using the left-hand rule, then we use the left-hand values in our function, and then multiply times the width of the rectangle, which is delta x. If we're using the right-hand rule, we use the right-hand values of our subintervals, and then plug those into our function while multiplying times delta x. The midpoint rule is plugging in the midpoint of each subinterval into our function and multiplying times delta x. Remember, our subinterval that I'm dealing with is x sub I comma x sub I plus 1. Therefore, the left-hand value in that rule is xi, and the right-hand value is xi plus 1. To get a midpoint, you add these two things up and divide by 2. This is the definition of the Riemann sum. Let a function f be defined on a closed interval from a to b, and let delta x be a partition of a comma b. Let ci be any value in the ith subinterval. The sum I equal 1 to n, f of ci multiplied times delta xi is a Riemann sum of f on a to b. Notice that the definition of a Riemann sum is a little bit looser than what we've been doing. We've used the left-hand value, the right-hand value, and the midpoint. This definition says let any ci be in the ith subinterval. Moreover, we've let delta x be a constant. This actually allows for different widths on the rectangles. We're not going to calculate anything aside from using the left-hand rule, the right-hand rule, or the midpoint rule. But the Riemann sum, again, is defined more broadly. So we can have lots of different Riemann sums on the interval from A to B. Let's go ahead and write and calculate the Riemann sum of f of x equals 6 minus x squared on the closed interval from 0 to 2 using 8 rectangles with the left-hand rule. Here is our problem. The first thing I want to do is figure out the widths of each of these 8 rectangles, which now we're going to call delta of x, come from the fraction. What we do on the top of that fraction is take the distance between 0 and 2, so 2 minus 0, and divide by 8 because we're dealing with 8 rectangles. So each rectangle is going to have width of 0.25. If I were to write a Riemann sum, let's go ahead and do that. I would start I equals 1 to 8 f of xi multiplied times delta x. You can rewrite these because now we know the delta x is actually a 0.25, utilizing the left-hand rule. And utilizing the left-hand rule, you can think about what types of subintervals you'd be getting. Our subintervals, our first one would go from 0 to 0.25. Our second would go from 0.25 to 0.5. Our third would go from 0.5 up to 0.75, and so on and so forth. You can see how the progression is going. These are our subintervals. Notice that if we're using the left-hand rule, we're going to write 0, 0.25, 0.5, 0.75, 1, 1.25. I missed one. I missed a, and so on and so forth. Let me split it into 4 intervals on top, 4 intervals on bottom. There you go. There is a way you could write this if you'd like. You could have written this as 0.25 multiplied times I minus 0.25. So when you plug in 1, you get a 0. When you plug in 2, you get a 0.25. When you plug in 3, you get 0.5, and so on and so forth. I am not concerned that if you're able to do that. In fact, I am just as satisfied if you write it like this, with x sub I, knowing that x sub I is the left-hand value for each. When we want to calculate this, we're going to have to be able to expand this out and, in fact, write out f of 0 multiplied times 0.25 and then plus f of 0.25 multiplied by 0.25 and then plus f of 0.5 multiplied times 0.25 and so on and so forth. I will finish writing these. Hopefully I don't miss one or more than one. One thing that we're going to be able to do is, in order to simplify our expression here, is notice that each one of my functions is being multiplied by 0.25. In other words, each one of these function values is multiplied times 0.25. That means if I want to do this in a little bit easier manner, I can factor out 0.25, and then my expression in here just becomes f of 0 plus f of 0.25 plus f of 5 plus f of 0.75 plus f of 1 plus f of 1.25 plus f of 1.5 plus f of 1.75. And that's all added up, and then you can multiply your final answer, or not your final, but you can multiply that sum by a 0.25. I'm going to plug those things in to my calculator, in fact, into this function here, 6 minus x squared, and see what happens. So we have 0.25 multiplied times 6, plus 6 is what you get out when you plug in 0. When you plug in 0.25, you get 5.9375. When you plug in 0.5, you end up with 5.75. When you plug in 0.75, you end up with 5.4375. When you plug in 1, you end up with 5. When you plug in 1.25, you end up with 4.4375. When you plug in 1.5, you end up with 3.75. And when you plug in 1.75, you end up with 2.9375. I'm going to add all those together and then multiply by 0.25 to get my answer. When I summed these numbers up, I got a 39.25. When I multiplied times the width of 0.25, I ended up with a 9.8125. Therefore, the Riemann sum using the left-hand rule gives us an approximation for the area under the curve, which is 9.8125. So this Riemann sum is a compact way to write this thing. And when I calculate it out in this example, I get an approximation of 9.8125. So there you go. That's how you use a Riemann sum, both notationally and calculating the actual number approximation. I would like you to push pause on the video and try this problem. Write and calculate the Riemann sum of h of x equals x to the third on the closed interval from 0 to 5 with 10 rectangles using the midpoint rule. Go ahead and try that on your own. In the next video, I'll do it.